Hello and welcome back to another VMK in the game development series. In this VMK we're finally going to be able to go in and implement the necessary functions that will render our COB files to the screen. There's actually a lot of work ahead of us, and I'm not going to lie to you. This is some pretty tricky stuff coming up here. It took me maybe, let's say, 2 or 3 days to come to the final code which I'm about to show you. It took me a few iterations to go through to debug it, as well as to be able to figure out how to make this work as efficiently as possible. I don't expect you to get it the first time through that you watch this video. You may have to watch this video a couple times to understand really what's going on behind the scenes. But let's go into PaintShop Pro here, and I'll give you an overview as to the general structure of what I'm about to show you. What we have done so far is we load in a COB file from Caligari, and when we do that, we automatically take all the data and dump it into memory. Well, now that it's in memory, we need to be able to take all of the data. So actually I'll put here dumped into Caligari file class. So now what we need to do is go through this Caligari file class and extract all the pieces that we need. And the pieces that we need are basically a node transform, we need a node shape, we need anything that has materials, textures, and texture transform. So whenever we find anything inside of this Caligari file, we need to determine which of these structures we want to create and how to initialize all the values inside here. So that's what we're going to be doing now. However, to do this, we're going to do it in the following manner. First thing we're going to do is go through this Caligari file and determine exactly how many materials, textures, texture transforms we're going to need to create. We're going to create one for every single texture, material, and so on that we have inside of the file. After we do that, we're then going to go in and for every single node shape, and then this guy will basically be using the GeometryCompiled class that we created in the previous VMK. So we're going to create this guy, and this guy is going to be placed inside of our node shape, and for every single material, texture, and texture transform that it needs to use, we're also going to link it up to the node shape. So the process is this. We're first creating memory for these structures, and then after that we're going to go through and actually create the node shape which contains all of these items. Okay? So let's go into our code and see how we can implement this. Back inside the scene class here, we have load Caligari file, and we did all the loading, and all the data is now stored in memory inside of this class here, Caligari file. You'll remember that I added this section here, more code will go here, and that's what we're going to be working on right now. Oh, there's one other thing I wanted to mention back here in PaintShop Pro. The structure that we're going to be using inside of the scene graph is as follows. We're going to create a transform right at the root of the scene graph, and we're going to call it whatever the name of the Caligari file that we're trying to load. Then underneath it, we're going to nest all of the data that we have stored inside memory. So for every single poly-H data that we have, we're going to be creating a new shape node, and that shape node will need to be nested underneath the transform. So the transform is going to contain all the translation, rotation, scaling data, and the shape node is going to contain all the material, texture, and texture transform data. So this is the structure we're going to be using to create our Caligari files inside of our scene graph. So to start off, we're going to need to be able to get the file name of Caligari file that we're loading in. However, you'll remember here, whenever we call load Caligari file, actually let's do a search here. Right here, you'll see that the file name includes the path. It may, or actually it may not. So if it does include the path, all we're interested in is the very last part here. So for this example, we want to get mech.cob out of the string. To do that, let's go back into here. This is the way we go and extract the data. We create a variable that will contain the path, and initially we set it to 0. We also need to get the path information because you'll remember that inside of the Caligari file, all textures are stored with an absolute path. However, that's not very useful if you start moving your games over to someone else's computer, because the textures, which will be maybe on your C drive on this computer, may not be on the C drive on your friend's computer. So because of that, what we're going to do is we're going to extract the path information for this specific cob file and then use it whenever we're loading in textures for the shape node down below. So first thing we do is we get the path information, but while we're getting the path information, we also might as well get the file name information as well. We create some memory to hold the path data. We initially set all the values of this array to 0, so there is no path. We also create a character pointer to something called pFileName. This is the guy that's going to be storing the pointer to the file name inside of this string here. So remember, this contained the path plus mech.cob. Well, once we're done, this value here is going to point to just the beginning of mech.cob. It's not going to have any of the path information at all. We also need another variable here, p/, which is going to be going in through the string here and looking for any slashes. And initially we look for backslashes, but if we don't find them, we then go and look for forward slashes. So let's take a look at how this works. I use a function here called strrchr. What this does is it looks through this string and it's looking for this specific character. And this character in the ASCII code, you'll see, is actually the backslash character. So as it's looking through this, it's starting from the very end of the string and working backwards. That's what the little R here is for. If I remove this R, then you're looking for the slash from the start of the string. But we're interested in the very last slash, so that's why we start from the back end. If p/ is equal to null, then that means that you've gone through the entire string, but you didn't find any slash character. So if that's the case, we then go and look for forward slashes, which is this one here. So again, we call strrchr, and we say we're looking through the same string again, but this time we're looking for a forward slash. Now you may be wondering why I didn't go in here and just type in single colon backslash single colon. You can't do that because this string here is actually an escape string. So what that means is the compiler actually interprets this as an escape key. So you use this whenever you want to specify things like a carriage return, which is a /n, or a tab key, which is a /t. So instead of using slash, I think you can also use double slash to give you the same thing as a slash. To avoid using that, I just ended up using 92 because I know 92 is the backslash character. Anyway, so going over here, we didn't find a backslash, we're now looking for a forward slash. If you don't find a forward slash, then that means that this string up here doesn't contain any path information, it just contains the file name. So if that's the case, I say that the path information is null, so I set that variable equal to null, and I set the pointer for pFileName, which is this guy right here, to point to the very beginning of our string. So now both of these are pointing to the same thing, which means that our file name is stored at the very beginning here. If we did find a slash over here, so this means we found a forward slash, then what I do is I use strncopy to copy a certain number of characters into this parameter here. If you take a look at this function inside MSDN, you'll see the following. we're using this first instance. The first variable contains a pointer to a character, so this is where we're going to put the result. Then the second value is a pointer to a constant character, and this is where we're going to be copying from. And the last parameter is how many characters we want to copy from the source into the destination. You can read through the description here to get a little bit more overview as to how this function works. But basically what we're doing is we're saying, take this parameter, put it into here, and this is how many different characters we want to put into there. The other thing we want to do is make sure that we store the file name. And to do that, all we do is we take the p/ value, which is currently pointing at the slash that we found, we move it forward one, so we add 1 to it, and we assign that pointer into p file name. So now this guy is pointing to wherever the string for the file name is located. So basically, if you had something like this, let me just write this out here. If you had file name, or sorry, file path, whatever, and then you had file name.cob, what p/ is going to be pointing to is this location right here, because it started from the end and it's working its way backwards looking for the slash. As soon as it finds it, it then goes into here, or at least it tells me where it's located, so we go into here. I want to save the file name, which starts over here, which is one more than the location of the slash. So that's why I add 1 and then I save that pointer to file name here. We do the same thing if we found a backslash. We copy the path information into our member variable, and then we also save a pointer to our file name, which is 1 plus the current slash location. Okay, next thing. Now we need to create the initial transform node, this one located right here, so that it can be used to nest all the other transforms underneath it. So I create a variable here called UI transform node, and this is going to contain the location inside of the scene graph for this transform node. I create a pointer to a node transform, and I use the new operator, so I create a new node transform. And I'm not going to set any values. The defaults are perfectly fine. But the one thing I do want to set is the name for this transform. And the name is going to be the file name that we saved using this variable up here. So we call proots set name, and we pass in the file name. And then after that, we need to save this transform node inside of our scene graph. And to do that, we use the add node function. We pass in the transform node we want to save, and then the second parameter is where we want to save it. Well, because we're saving this at the root, we specify 0 here, and then that's it. The return value is our unsigned integer for the location of our root transform. This unsigned integer up here is another unsigned integer which we're going to be using a little bit later. So actually I'm going to move it down here just to make it a little bit easier to see where things are grouped. Okay, now we go into our major for loop. This for loop is going to be going through all of the Caligari files poly-h data that we've saved in memory. You'll notice that our variable that we're using through this loop is IP. IP because I indicates the index of the current poly data that we're working with. Remember that because you'll notice down below I use quite a few for loops, and I try to sort of name the index values appropriately because things get confusing very quickly. Alright, first thing we're going to be doing is creating the transform node for this poly-h data. So again, if we go back here, we've already created this transform here, and now we're interested in creating this one right here. So again, we use the new operator for a new node transform. If there's an error, we just generate an error message and then we continue. Alright, if we've successfully created this node transform, then we need to set the name for this guy, and the name of it is going to come from whatever we have in memory. So we take a look at the current poly-h's data, so we use the index here to dereference our member variable here, which is our array of all the different kinds of polys we're working with, and we're going to be using the getName function to get the name of the poly-h data. If we go back into here, poly-h, you'll notice we had a getName function which basically returns a pointer to our name that we got saved originally. So we return the name and then we save it inside of our transform. We then go in and say we do have a matrix for this transformation, so we want to go in and save the matrix data from the polyh data and put it inside of our node transform. Finally, we call add transform, where we pass in the p transform, which we just finished creating here, and we're saying we want to nest it underneath the root, which was the original one here that we created. Now, you may be wondering, what is this set transform and what is this bHave matrix business? If you go inside of node transform, you'll notice we don't have these variables. Well, we don't have them because we haven't programmed this in. This is actually new stuff. We have to go inside of the node transform and make a few modifications to it so that it can support the Caligari format. Now, we don't want to disturb this node transform too much because we still want to use it exactly the same way that we've been using it up till now. We want to be able to translate, create scales, create different rotations, things like that. But we also want to use this node transform for all the data that we'll be getting from the Caligari file. So to facilitate this, we need to add the following. We need to create two new variables. We have a Boolean, which says whether there's going to be a matrix in this node transform or not. And we also need an array of 4x4, or actually 16 values, to contain our transformation matrix. Then we have to go up here and create a new function, which is setMatrix. And all this is going to do is take the transformation matrix that gets passed in here and save it inside of this member variable. So let's save that and then go inside of node transform. Inside of the constructor, we should initialize those new member variables we just created. By default, we're going to say we don't have a matrix, so we set the variable to false. And we also need to initialize our transformation matrix to something, so by default we're going to set it to the identity matrix, which has 1 on the diagonals and 0s everywhere else. Now, the other thing we need to add in here, and I'll put it right underneath the update, is our set transform. Actually, I renamed it to be set matrix, so let's just comment this out. Alright, and then what this does is it sets a transformation matrix equal to whatever's passed in. So we're taking the 0, the 1, the 2, all the way up to the number 15 index and saving all these values inside of our member variable. Now that we have the transformation matrix, we need to make a few modifications inside the render OpenGL so that we can use this matrix data when rendering a node transform. And to do that, all we do is between the GL push matrix and the first translate function call here, we add the following. If we have a matrix, so we check that variable we just added, if it exists, then we want to call GL multiply matrix F, and we pass in of the 4x4 matrix, which we have data saved for. What this is going to do is it's going to take the current model view matrix, multiply it by this 4x4 matrix to give a new result. Then, after we do that, we can apply the translate, rotate, and scale and all this other stuff the same way we've done before, and everything will continue working properly. So, those are the modifications we need to make to node transform. Let's just go and compile this, make sure we didn't introduce any errors. Okay. So that looks okay. We can close that off now and return back to, where were we? Scene.cpp. Okay, now here's where things start getting messy. We have another for loop. But before we get to that, we need to create a lookup table for all the material IDs that we're going to be working with. So to do that, we created std vector, which is going to contain chunk material IDs. So I call this v material IDs. And initially, we clear this to be empty. Now you may be wondering, what is this chunk material ID? We haven't defined it yet, so we need to go and create it. This structure I'm going to place inside of Caligari poly h.h. Just put it right here underneath all these other structures that we've created. So what it's going to contain is a short value to a material ID. This is going to be the material ID number from the Caligari file, but it's also going to contain the unsigned integer values for the material ID, texture ID, and texture transform ID that the scene graph uses. So in a way, it's a lookup table between this ID number, which is Caligari's format, and these values here, which is our own scene graph format. Okay? Then, let's go into a second for loop. And this for loop goes from 0 all the way up to the total number of materials we have saved in memory. So remember, this was an array structure that contains all the Caligari mat1 data that we read in from the Caligari file. First thing we need to do is find the specific material that is referenced to the current poly H data that we're working with. Remember, we're working with all the different poly H datas one at a time. Initially we start at IP equals 0 and we work all the way up. So what I do here is I have an if statement that says check this poly H data's ID number, and if it's equal to the material ID's number parent, then we know that this material is the child of this poly H. So in other words, this material belongs to this poly H data. If that's the case, we can then go do some work. And the first thing we do is we need to go and save the smoothing angle and the material ID number used for this specific poly H. And to do that, I created a function called setSmoothing, and this guy just basically takes in a smoothing angle that we have stored inside of the material data and also the material ID number that was stored for the specific material data. So we pass these two values into our function called setSmoothing, and that's stored now inside of poly H data. So we need to go in and create the setSmoothing function inside poly H. You'll notice that I'll be going back and forth between these classes and adding new functionality into them because we now need them as we're creating everything dynamically. I didn't want to do this earlier when I first created these classes because you would have been very confused as to why would I even need this function. So that's why I'm doing it now. Alright, so inside Caligari poly H, we're going to add our setSmoothing function, which takes in two values, the angle in radians for the smoothing angle and the ID number for the material. Now we need to go into the CPP file, and right here at the bottom, we'll add the setSmoothing function. So this guy stores the smoothing angle for the material ID. This information is stored in a structure that will be used to determine how many different materials are used with this specific poly H. And this will make more sense in a little bit. So inside here, what we do is we create a new structure called material angles. And what this contains is three things: the smoothing angle in radians, the material ID that's used inside the Caligari file, and this Boolean variable be required. Don't worry about this be required just yet. I initialize it to false, but it will be used a little bit later inside of a function called getNumberMaterials, which we're going to be implementing in a minute. So this won't make any sense just yet. But these two values we're basically just saving inside of the structure. Now this structure is new, so we need to go and create this one as well. So once again, we're going to go inside Caligari polyh.h, and at the top here we're just going to add that new structure. So it contains a short, which is the material ID, floating point number for the angle, and the Boolean for the required field. Okay, so where were we here? We take all those things, and oh yeah, we also have another member variable here inside of Caligari polyh, which will store all of the data here inside of an array. So we need to create this guy here as well. So going back to Caligari polyh.h, and I'll just put it right here. So it's an std vector of all the material angles, and that's the name of the variable that we're going to be using. So we just take this guy and we push onto the stack this current value here that we've just saved all the data for. So that should be it for here. Let's just make sure we can compile this and we haven't forgotten anything. We haven't broken anything here, so that's good. Now we can go back into scene.cpp and continue on through. So we found the material that belongs to this poly H data. We've stored the material ID number and the smoothing angle. Actually, did we have a get angle function inside material? No, we didn't. So we need to go and implement that as well. So going inside Caligari mat1.h, we're going to have to add some functions here. Let's put it right here. We're going to need to create a function called getAngle and getMaterialID. Again, if we go here, we see we have getAngle and we have this other function getMaterialID. So we implement these, and inside here, let's go and actually write those functions. Nothing too special here. We just return whatever the member variable is that contains the angle, as well as the member variable that contains the material ID. Save that and make sure we can compile this guy. He looks okay. So we can now go back into, where were we? Scene.cpp. Okay, so here we go. Next thing we do here is create this material variable, which we'll be using to create the material that's stored inside of the Caligari file. So we call the new operator, and again, we check for errors. And the other thing we do here is we create two new variables, one for the texture ID and one for the texture transform ID. Initially, we're going to assume that both of these are not existent, so we're going to set these to 0, but a little bit later we're going to do a check inside of the shader box class to see if there was a texture or a texture transform. If there were, then we need to go and assign values to these guys. Okay, and speaking of the shader box, well, guess what? We need to go through all of the Caligari files shader box data that we saved in memory and figure out which one of them is associated with the current material that we're working with right here. So remember, we're inside of a for loop IM that specifies the current material number that is associated with this poly. Well, now we also are going to be doing a check to see which material number is associated with this shader. So again, we do the same thing. We check the ID number for the material to match the parent ID number of the shader. When we find a match, then we know we have all the data we need now, because we have IS pointing to the shader data and IM pointing to the material data. So using the combination of the two, we can then go and extract all the color and parameter information for all the data that needs to get saved in pMaterial. And pMaterial, again, was this variable up here, which is our own material structure that we use inside of our scene graph. So what we do is we start off with the ambient values, and we're going to be taking the material data's color, so IM is the current material number that we're using, and we're taking the color value, and we're going to multiply it by the shader value's diffuse value. You'll remember we didn't really have an ambient factor stored inside of Caligari file. Actually, ambient, what was called ambient was actually this equivalent of emissive for us. But what we're going to do is we're going to use the diffuse value here and just save whatever the color is for the diffuse into the value for the material here for ambient. We're going to do the same thing for diffuse. So again, we take the color from the material section and we take the diffuse value from the shader section, multiply them together and save it inside of a material. Notice that the alpha value is always the same value, and it's coming from the last parameter inside of the color. For the emissive part, we take the color from the material, and this time we're multiplying it by the emissive factor stored inside of the shader box. For specular color, we did have our own specular color parameter, so we can take that from the shader box data. We take color, specular color 0, 1, and 2, save that in there, but the alpha value is coming from materials color fourth parameter here. And then finally we have our shininess factor. Caligari only saves the shininess between 0 and 1. However, OpenGL uses a value between 0 and 128. So what I do is I just take the 0 to 1 range, multiply it by 128, and then that's our shininess value that we're going to be using. So you see here, we're taking the shader box value for shininess, multiplying it by 128. Okay, up till now, all we've done is we've saved the color information for the material data. However, if the material contains a texture or texture transform, we need to be able to handle that as well. So, to do that, we go through the following. We check to see if this material ID number has a texture, so we call it isTextured. Now you'll notice that we don't have an isTextured function just yet inside of material 1, so we need to go in and implement it. To do that, you can just go inside Caligari 1.h and add a function that returns a boolean that is called isTextured, and then inside of the Caligari mat1.cpp, I've just added it here. We return the member variable that's called bTextured. And this contains true or false depending on whether there's going to be a texture with this material or not. We can then go and create a new member variable for textures and call the new operator, and we pass in the following parameters. We say we're going to be using MIP mapping. We're going to be always using quality factor 4 for now, and we also specify whether this texture is solid or not. And that information was stored inside of the shader box data. So if we open up this guy, you'll notice there's a member variable MBSolid. And this guy will tell us whether alpha value contained transparencies. So we pass all that information in, check for errors. Now what we do next is determine which file to load into this texture structure. So what we do is create a new variable here that is going to contain the path plus the file name information of the texture we want to load. So we take first the path information. This was stored for us way back here outside of the original for loop. You'll remember we created this path information based on the file name that was passed inside of this function load Caligari file. So once we have the path information, we just concatenate it with the file name of whatever stored inside of the shader box. And the file name only contains the file name of the texture. You remember we stripped out the path information whenever we saved the file name for the textures inside of the shader box. So once we have this new variable here, we can then go and pass it into our load texture function, which loads this texture into our texture pointer and then returns a texture ID number. If the return number is equal to 0, then something bad happened inside load texture. Then we call continue to break out of our for loop and continue on processing the next chunk. If we didn't get 0, then the texture was stored and we can continue on. Now the last piece is to determine whether we need a texture transform. And we only need a texture transform if the offset or the repeat values are not equal to 0 or 1 respectively. By default, our textures are rendered with assuming that the offset is located at 0, 0, which is bottom left-hand corner, and the repeat is set to 1, 1, which means we're going to texture the image onto our surfaces only one time across each dimension. If the shader box data indicated that we don't want to use 0 or 1s, then we need to create a texture transform to accommodate for this. So if we do go inside of this if statement, we create a texture transform, use the new operator to create it, and then we need to set the center and the scale values of the texture transform. And the values are coming out of the shader box data, so we take the offset for S and T, save it inside of the center's X value and Y value, and then the repeat values are saved inside of the scale 0 and 1. And then finally, we also need to call save texture transform, which will go in, take this texture transform data that we just created, save it inside of our array, and return our ID number for the specific texture transform. And that's it. Now we just need to go in and clean up all the missing brackets that we have for all of the if statements and for loops that we opened up. So be careful here. You may run into a few problems when doing this. I know I did. So let's see. I tried labeling my brackets a bit so that it's a little bit easier to figure out where the errors may be happening. So this one is for if needs to be a texture transform. If you follow it up, you'll see there's the if statement. This one is if it's textured. If you follow it up, here we are, if it's textured. And then if it is textured, we just break out because we're done with if found shader for this material. So if we follow this guy up, we see there was a shader for this specific material. And then the next one is the for loop for all the shaders. So for all the shaders here. Now up till now, we've saved the texture transform and the texture data because we've gotten the ID numbers, but we haven't saved the material yet. To do that, we need to use the following. I create a structure here called chunk material ID, and by the looks of it, I think I've already defined this somewhere. Let's just go quickly look for the definition. Yeah, it was this structure here which contains the material ID as well as the ID numbers for the material, the texture transform. So now what we do, so we take the material ID number from the material, we save that inside the structure, we take the material we've built up till now and we actually save it inside of our scene graph, and the return value is the material ID number that we're going to be using. We save that inside of the structure. And then we also save the texture ID and the texture transform ID. You'll remember that back up here, I created variables UI texture ID and UI texture transform ID, and we set them to 0. So if we don't have texture transforms or textures for this specific material, it's okay because we have the variables already set to 0. If there were some textures or texture transforms, then we loaded them in and we overwrote those zeros with the appropriate ID numbers, which we then can go and save inside of the structure. Last thing we do is we actually take the array which contains all of the chunk material ID numbers, and we save these current values onto that array, so we call pushback. Alright, so we've saved the material, we've saved the texture transforms, and we've saved the textures. What do we need to do next? Well, first thing, we should clean up some of our brackets again. Let's see here. This should go here. So if found a desired material, if we scroll all the way up, you see here we go, and then this for loop is for all the materials that we looped through. So I labeled here for all materials. Now we are back inside of our original for loop, which is for every single poly H data that we're working with. We've saved all the material data. Now all we need to do is make the linkages between the material and our node shape. But before we do that, there's one thing we shouldn't forget to do is calculate our normals. Caligari does not save normal information inside of the Caligari format. So as a result, what we need to do is calculate the normals and save them inside of our structure ourselves so that we can go and render things whenever lights are turned on. So I created this new function called calculate normals, and we put it inside poly H. So let's go ahead and do that right now. I'll just put it here underneath set smoothing, calculate normals, and inside the CPP, we'll just put it right at the very bottom. Okay, this function is going to be responsible for calculating all the normals for every face inside of our poly H. And it's also going to be responsible for averaging the normals per vertex if smoothing is enabled. But for now, we just want to get something rendering on the screen, so I'm not going to do this last part. I'm just going to calculate the normals per face. We'll come back to this function in the next VMK and implement the smoothing. Smoothing is a little bit extra math, which I don't want to get into right now. I just want to be able to render things to the screen. So first thing we do is create a variable here, if, which is a general index that's going to be working for each face. And I set it to 0, and I go through every single face that's stored inside of our poly H data. For each face, what we're going to do is create a new plane. And the plane itself is described by 3 vertices, so we need to take the 3 vertices of every single plane, pass it into our plane constructor, and then our plane is going to actually calculate the normals for us, which we can then use to call getNormal for the plane, and we're going to save that inside of this container here, MV normal face. So MV normal face is going to contain the normal for every single face that we need to render. And then a little bit later on in the next VMK, we're going to add more code here to smooth out the normal so that we get smooth surfaces for every single object. But for now, we're just going to leave this out. Now, a little bit more explanation here may be needed. If we look inside of our math lib, we have our plane, and we had two different kind of constructors. We had this one here and this one here. The first one was a point in the normal, and the other one was 3 points. So if we pass in 3 points, then it calculates two vectors, crosses them to get the normal, normalizes them, and so on. So that's going to work great. However, we're in here. However, we need to be able to have 3 vertices. And the 3 vertices need to come from our poly H structure. You'll remember inside of the structure we created this vector which contains all the vertice data. Now the vertex that we're interested in for this specific face is stored in another structure called MV face. And the current face that we're working with is indexed IF. So we're taking the current face, and the index that we're interested in is number 4, number 3, and number 0. According to the Caligari file spec, you'll remember there was this one variable which was 6 values long, which contains the vertex indices as well as the UV index data. The vertices were 0, 2, and 4, and the UVs were 1, 3, and 5. So we're pulling 0, 2, and 4 out to get our 3 vertices for our face. We had a constraint in our loader that said all of our faces had to be 3-sided, which means we have 3 vertices per face. So that's why we only are worried with 0, 2, and 4. So we take the indices values out of here, we use them inside of this array, and then this array will return to us a vector 3 which contains the x, y, and z coordinates of each vertex. So it's a lot of nested math here, but hopefully it makes sense. And then finally we call getNormal, which returns the normal value that the plane constructor calculated for us, but now we're pushing it onto this new member variable called m_v normal face. We need to go and create this. So let's go into here and create that container. I'll just put it right here. It's just an std vector of vector 3s, and it's going to be called m_v normal face. Okay. Where is my CPP? Here's my CPP. Let's go and try to compile this, make sure it's still okay, which it is. So now we can go back here, calculate normals. We have our material saved, we have our texture saved, we have our texture transform saved, and we've calculated all of our normals. Now we just need to go and create the linkages between a new node shape and all of these pieces that we now have. So to start this off, we create a variable here called number of materials, and this is going to contain how many different materials this poly H is using. So we create a function called getNumber of materials, and it's going to return a number. We need to go into our poly H and actually create this function. I'll put the definition of it, how about right at the bottom. And inside of the CPP file, here we have getNumber of materials. Now this function is going to return the number of materials this poly H chunk uses, but it also checks to make sure that all required materials are already stored in the material1 data structure. If there's a mismatch, then we have an error because we can't actually create this specific node shape. First thing we do is we check to make sure that we have some faces. If we don't have any faces, we're not going to have any materials, so we can just return 0, saying we don't have any materials to use. If the size of this is not equal to 0, we need to go through every single face and determine what is the material ID number and compare it with what we've already have saved. So this is how we do it. We create a variable here called beFound. We initialize it to false, and then we go through all the material angles that we've saved inside of our material angle structure. You'll remember there was an extra parameter that we used to specify whether it's required or not. this is where we actually use it. So if we find a material for a specific face to match a material that we've saved inside of our structure, then we say we have found something, and we also say that this material is required, so we set it to true. After we find a match, we break out of this for loop, and then we go down here. So if we didn't find anything, we generate an error message saying this specific face requires a material ID number, but mat1 is missing for this face, so we don't actually have the material data. So this initial for loop is going through and it's tagging all the materials that we're going to be needing as required. Then, after we go through that first for loop, we then go into this while statement. And inside this while statement, we go through and we look for all the materials that are not required. If they're not required, we can go and erase them because we won't need them. So we just go and remove them and erase them. If we do need them, we go and increment our counter. And we continue doing this until we've gone through all the saved materials. After that, we can then go and return the size of this container here, because this container now contains exactly how many materials we need. We've removed all the ones we don't need, and the ones we do need we've tagged as required so that up here we increment our counter. So it's a little bit convoluted, but the general idea is it counts how many materials this specific poly-H uses. So now, going back into here, we have a for loop that goes through 0 all the way up to however many materials we are using. For every single material that we're using, we need to create an independent shape node, because each shape node is going to contain geometry that uses that specific material, as well as the material structure and maybe texture and texture transform data. So it is possible to have one poly-H data using many different kinds of materials. For instance, a cube, and paint each of the 6 sides a different color. If you do that, then you'd be using 6 different materials, and then all those materials need to be nested underneath the same structure, so that's why we needed to create this sort of arrangement. So inside of this for loop, I create 3 variables to contain the current ID numbers for the material, texture, and texture transform, which we want to be using for this specific material. Next thing we need to do is actually find the material that we have saved in memory and extract the ID numbers so that we know how to create the scene graph structure. First thing we do is we go inside of the poly-H data structure and we pull out the material number that index whatever this for loop is specifying. So initially it's going to be 0, and then next one, next one, next one. And each time we're going to return the ID number for the material that Caligari is using. Now, I don't think I've implemented get material ID just yet, so we need to go inside poly-H and implement it. And I'll put this right underneath our previous function. So we go into our m_v material angle structure and pull out the material ID number that Caligari is using, and we just return that. So back in here, then what we do is we go through all of the material IDs that we have saved and look for the one that has the matching material ID number. So again, we're going through every single one using this for loop, and we're looking for the match. As soon as we find the match, then we extract the ID numbers for the material, texture, and texture transform that the scene graph is going to use. This gets very confusing because we have material ID numbers from Caligari file and material numbers from our own scene graph. Anytime Caligari files are being used, I've used an S in front of those, but the ones that we use inside of our scene graph, we use unsigned integer, so you see UI in front of those variables there. So anyway, once we find them, we save them inside of these variables here, and we also tag be found to be true so that down below, which is coming up next, we can do some work. If it wasn't found, we generate an error message saying that material ID whatever doesn't exist. We continue on through to the next guy. Otherwise, we then go and create our GeometryCompiled structure. Now remember, this was also created in the previous VMK, so now we can go ahead and use it. So we use our poly-H data, and we call a function called createGeometryOpenGL. And we need to pass in the material ID number, texture ID number, as well as the smoothing value that's this poly-H data is using. The return value for createGeometryOpenGL is a GeometryCompiled pointer, so we can just assign those to be equal to one another. Now, because we haven't implemented this yet inside poly-H, we need to go and do that as well. Let's go into here. And also on the bottom, I'm just going to put it right here. So we pass in the material ID, texture ID, and the smoothing, true or false, and it's going to return to us a GeometryCompiled pointer. Inside of the CPP, let's actually go and implement this function. Okay, so what this function does is it creates the geometry using OpenGL and a display list. Only faces that use the material number S material ID are selected inside of this creation process. So we pass in our material number, our texture ID, and be smooth. And actually, let me go back here for a second. Is smoothed. We haven't implemented this function because we haven't wrote the code to do the smoothing just yet. So for now, let's go and take this out and just set this to false. Because you remember, we only created normals for every face. We haven't created normals to give our surfaces nice smooth shading. So we'll come back to this in the next VMK, but for now, just change that to be false. Alright, so in here, what we do is we create a pointer to a geometry compiled structure. And we call the new operator, and if there's an error, we just return null, because null means that we don't have any geometry compiled pointer. So actually back here, if null was passed in, then we won't go into this if statement and nothing else will happen. Otherwise, if there wasn't any error message, we set bTextured initially to false, and we check to see whether the ID number for the texture ID that was passed into here was not equal to 0. If it's not equal to 0, then that means we are using a texture, so we need to quickly just change the variable to be true. The way that the geometry compiled structure works is you need to call start record at the very beginning and stop record at the very end. And in between those two function calls, you need to call all the OpenGL functions that will actually render the object to the screen. And as you're calling those, what's happening is all those functions are getting compiled into a display list, which we can then go and use to render. So we call start record at the top, and then we go and begin rendering all of our triangles. Remember, Caligari format, we've specified we can only render triangles or three-sided shapes. So that's why that's the restriction that we've chosen. In here we say we're going to be rendering triangles. If we're using textured, we do one thing, and if we're not using textures, we use something else. So let's take a look at the non-textured case first. We check that smoothing parameter. I've taken the code out here for now because by default we've always passed in false into the smoothing parameter here, since we don't have the normals calculated properly anyway. So we're going to go into this else statement here. What we do is we go into a for loop for every single face that's stored inside of our poly-H data. For every single face, we check the material ID number for that specific face. If the material ID number matches the current material ID number that we're working with, then we want to render that specific face. So to render it, we first set the normal up. We call GL normal 3F, and we pull the normal face's value. So this current face's normal value for X is this, for Y and for Z. And then we also need to call GL vertex 3F for the three vertices that make up the face. And the three vertices are saved inside of this structure here, but the indices are stored inside of this structure here. So similarly as we did before, we need to dereference the current face, then we call 4, 2, and 0 to get the three vertices, and then we use X, Y, and Z to get the three parameters. So that's what you see me doing right here. One thing I forgot to mention earlier is Caligari saves all of its faces in clockwise winding order, which is bad for us because in OpenGL we've specified by default that clockwise winding is the back face of a triangle, and you won't actually see it being rendered to the screen. So to actually make things render to the screen, you need to reverse the winding order of your vertices, and that's why I have them backwards here, 4, 2, and 0. By using 4, 2, and 0, we ensure that the vertices are unwound to us in a counterclockwise order so that when we do render them, we will see them on the screen. Okay, so we go through the for loop looking for every single face that has the specific material ID number. If we find it, we specify the normal, specify the vertices, and we render it. At the end, we call GL end, and then after that, we call stop record, which stops the recording process for the compilation of the geometry compiled structure. Then we just go and return our pointer to our geometry structure, which we will use in a second. But before we go any further, let's go and take a look at the textured stuff. It's basically the same stuff that we have here with the added complexity of our texture coordinates. So again, I've taken out the code here for the smoothing part and instead just left the code here for the non-smoothing stuff. So again, we go through a for loop for every single face, looking for the materials to match. When we find the matching materials, then we specify the normals, x, y, and z, and then for every single vertex, there's 3 of them, we need to specify the texture coordinates as well as the vertex coordinates. So now you can see here we're using 5, 3, and 1, which is the UV coordinates, and 0, 2, and 4, which is the vertex coordinates. So we're passing in the x and y for UVs and x, y, and z for the vertex coordinates. Alright, so that's how we compile our geometry. Now let's go back into here, and after we have it compiled, if it returns some value that's not null, then we know it all succeeded successfully. We can then go and call save geometry, and this will go in and save the current geometry inside of our scene graph structure. We don't need the unsigned integer value that gets returned here because the constructor for node shape actually needs a pointer to a geometry. So we just pass in our pointer to geo here directly into the node shape constructor. If this succeeds, we can then go on through. First thing I do is I call add node, which immediately nests this current shape node under the transform node that we're working with. And this transform node, you'll remember way back at the beginning, was the transform node we created for the poly H. This time we do save the shape node ID because we may need it if there's any material, texture, or texture transform data that needs to get saved. So that's what we check next, is we need to go in and assign a material for this specific shape. So I do that here. I specify here's the shape ID, here's the material ID. If we have a texture, which would be a value greater than 0, then I'll also call assign texture. And if there's a texture transform, then I call assign texture transform. So all of this creates the linkages between our node shape and all of the material, texture, and texture transform data. You'll notice that I always attach a material to this shape because Caligari does not save any data without a material structure. So I'm guaranteed that I will always have this guy. You could add an extra check in here to make sure that unsigned integer material ID is greater than 0, but I just didn't bother because I was getting tired of programming. You'll notice we've done a lot of code in this video and we're still not done. Now it's just a matter of closing off our brackets that are missing. So if we do this, we should close off all our brackets. Here we have else if there's an error. We have a closing bracket for the for loop for all the materials, and then a for loop for all the poly H. So there we go. That's how we load the Caligari file and actually put all the data inside of a nested structure. Let's go and try to compile this, and hopefully everything works. Spoke too soon. Let's see what we have here. Okay, we're missing a definition here for geometry compiled. That's easy enough to fix. We just need to go up here and include the following. Let's go and compile poly-h. Okay, that's good. Now let's go try to compile scene.cpp. Still a few errors. Cannot convert parameter 1 to Boolean. Okay, let's take a look here. Our first parameter for texture is a pointer to our error handler, so we need to add that. The second guy is mip mapping, third guy is quality, and the last guy is solid. So I just missed the first parameter here, which is okay because I think we're inside scene, and scene actually has our pointer value. Let me just double check here. Yeah, it's right here. So we can just go and call mp error handler. Two more. Get file name. Okay, we're missing a function called get file name located inside of which function here? The shader box. So let's go and add it. And we'll also need to add it inside the CPP. Let's compile this guy, make sure he's okay. And then let's try scene.cpp again. Okay, now let's build. And it worked! Alright, let's go and run and see what happens. We have our boxes, and we have some sort of mech laying on its side. Okay, so our Caligari file is loading and parsing data correctly. Now let me address what's going on here. First of all, let's go actually take a look at our mech model inside TrueSpace. So then we can compare to see whether what we're rendering on the screen is what we're expecting. Okay, here we are in TrueSpace, and I've loaded the mech.cob file, which I'm using. Now notice one thing. The mech itself is standing upright on the grid. He's not laying sideways, and he appears a little bit dark. So what's going on here? Inside of our renderer, our mech was rotated 90 degrees on its side, and he wasn't quite so dark. Well, if I do a render, you'll notice that he actually brightens up. And if I open up the material editor and select any of these material things, you'll notice that the material itself is comprised of a color, which is this reddish color. It has a reflectance shader, which has all the parameters that you need here, but it also has a bump map. The bump map gives our mech inside TrueSpace here sort of a more three-dimensional look. If I render this again, you'll notice that there's extra detail here on the arms and stuff like that. So we're not going to get that because we're not using a bump map. But the other thing is the reflectance shader has, by default, currently been selected to something that has all these different kinds of parameters. It has reflection, transmission, refractance, and all this stuff. Remember, we only support luminance, diffuse, shininess, specular parameters. These other ones we don't really care about. So what might be helpful is you could go in here and change it to be the default Phong, and when you do that, you can see that our mech all of a sudden turns that color that we are using inside OpenGL. So it's a matter of we're not supporting the default settings that this mech is using. I just pulled this mech out of a material library that came with my version of TrueSpace. So I didn't create this guy. I don't exactly know the details of what kind of materials this guy used, whoever designed this mech, but it does contain bump mapping and reflectance shaders that we're not supporting. So that's basically the reason why the colors and things like that don't match up exactly to what we see inside of OpenGL. But the more important thing is, why is the mech sideways inside our renderer, whereas it's not sideways here? Well, take a look at the coordinate system. Let me open this guy up here, and let's take a look at the x. If I take the x value and I start changing the position of our mech, if I'm moving it along the x, that's the green axis, he's sliding sort of forward and backward. If I'm moving the mech in the Y direction, he's sort of moving forward and back. And if I move the mech up and down, that's in the Z axis. Now, in OpenGL, X is left and right, Y is up and down, and Z is in and out of the screen. So you see, TrueSpace is using a completely different coordinate system than OpenGL is. X is fine, it's left and right, but in TrueSpace, Z is up and down. However, in OpenGL, Z is in and out, which is the equivalent of Y. So to fix this, we need to do a coordinate transformation. And I thought about different ways of doing this in our code implementation, but I ended up boiling down to a couple lines of code in one function. Rather than implementing an extra transformation matrix to be nested underneath our current structure, you can get around all of this by just flipping a couple of values inside of the transformation matrix. And by flipping them, everything else still continues working exactly the way that you would expect it to. The coordinate system inside TrueSpace is as follows. Positive X is this way, and positive Y is this way. And we can see that just by moving our object. So if I move it along the X-axis, watch the X value over here inside of the dialog box. If I move it to the left, it's getting larger. And if I move it to the right, it's getting smaller. So positive is this way. And then Y, if you look at the Y value here, if I move it forward towards me, it's going higher. And if I move it away from me, it's getting lower. So positive Y is this way. And positive Z is upward. As I move the mech upward, you notice the number is getting larger. And if I move it downward, it's getting smaller. So that's coordinate system for TrueSpace. But in OpenGL, we have positive X to the right, positive Y up, and positive Z forward. So if we go into PaintShop Pro, I've drawn out these coordinate systems here. You see, this is what we want. We want X, Y, and Z this way, but this is actually what we have saved in the Caligari file. X to the left, Y forward, and Z upward. So what we need to do is look at these things and make a correlation between the values that we have saved with the values that we want. And the correlation is actually quite easy. Anything that we have on the X values is actually the negative of what we want. So if we had some point located over here, let me just get a marker. Let's say we had a point sitting right here on the X-axis. Well, that would be somewhere over here. So if we had something like positive 5 inside of our Caligari file, that would be negative 5 inside OpenGL. So we just take the negative value of whatever we have and save it inside of our data. Next thing, let's say we had a point located up here on the Z-axis. So let's say this was Z equals 3. Well, for us, that's equal to Y equals 3. So all we need to do is take any Z value that's saved and instead save it as a Y value. And the same thing goes with Y here. If we had a point along the Y-axis, let's say Y equals 2, that's equivalent to Z equals 2. So we flip Y and Z, and we negate the X value. If we apply that transformation, we'll convert from TrueSpace coordinate space to OpenGL coordinate space. So let's go back into Visual Studio now, and inside Caligari polyh.cpp, we created a function called setTransform. And you'll remember here what we did is we just took all the transformation data from row 1, 2, and 3 and saved it directly inside here. Well, now what we want to do is modify this slightly to accommodate for that transformation that I just described. So now what we're going to do is we're going to apply a negative for R1 and then flip R3 with R2. So you notice R3 is now in the Y position and R2 is in the Z position. And the way we do that is we just apply a negative to all the X values. So this is X, this is X, this is X, this is X. And then Y and Z, we just flip. So we now have row 3 up here rather than row 2, and row 2 down here rather than row 3. So these two have been flipped, and this one has been negated. So you apply that to all those transformations, and now when we go and compile and run, our mech should be standing upright in our scene. And it is. So there we go. We now have a fully functional Caligari file loader. If we wanted to go in and load other file formats, it's just a matter of going through our code inside of our scene. Let's see if I can find it quickly. Scene, initialize. Now it's just a matter of going in here and calling load Caligari file for any other COB files that you want, and you'll automatically load them into memory, parse them, do all the stuff required, and populate the scene graph tree. Alright, and I'm done. This video is probably going to be very long. I'm not sure how long it's going to be, but I have a feeling it's going to be one of the longer ones. So, hope you enjoyed it. I'm sure some of you will have questions. Feel free to go to the website, post your comments inside of the forums if you get confused with something or if you just can't get anything working. I am going to include this mech.cob file for you inside of the VMK so that you can use it whenever you want to render things to the screen. But I would highly recommend you download GameSpace, go and play with it, create your models in there, export them as COB files or scene files, doesn't matter. This loader will support both. And then once you're exporting them, you can go and play around with adding items into your game engine. Okay? Once again, if you find my videos helpful and you can support my website, you can do so by clicking on any of the PayPal icons found on the website or any of the Google ads.